Hello, everyone, and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker's developed in order to help scientists discover the world around us. Today's topic, we're coming back to the X4 POSEIDON. Now, what is the X4 POSEIDON? Well, it's our brand new X-ray microscope that's designed to fit everybody from a novice all the way up through an expert user. And with that versatility, the idea is to really offer something that can replace the conventional microscope in really every lab. Now, in order to learn a little bit more about that product, we've put together a video. But for the rest of the Live from the Lab for today, we're going to go over a bunch of different examples with one of our experts here at Bruker in order to see some of the applications that this can be used.
Hey everybody, thanks for joining. My name is Billy Reese. I am the X-ray microscopy application scientist here at Bruker. So super happy to be back for Live from the Lab today. And rejoining us here is John. Hey John.
Hey, Billy. Just going and picking up our awards that we happen to win for the X4 POSEIDON.
Would you mind telling me how you got these? These are beautiful.
So, for our video actually that we put together to introduce it, not this video that we just watched, but the other video that we put out for the X4 POSEIDON talking about how it could be used for just general microscopy, we actually won 2 awards. So Telly Awards. So that was pretty cool.
That's all. I mean, and yeah, look. I didn't do the videos, but it was for the X4 POSEIDON, so I feel like I had some kind of part in this.
Yeah, I mean, it's a team effort that all this stuff is.
So these are your awards, they're, kind of my awards.
Well, it's the whole team, so both here and then also at our partner Scene Factory. And I think, though, what this also speaks to is that idea that X-ray microscopy is becoming more and more a mainstream topic. And that's kind of embodied in today's episode, where we're going to talk about all different applications.
Yeah, absolutely.
Now, speaking of that, though, Billy's not expecting this, but you actually kind of are tied with the X4 POSEIDON because you started your journey here at Bruker.
That's right.
About when the X4 POSEIDON was finishing development and then moving into being a product, right?
That's right, yep.
So, 2 of you kind of intimately tied. How's it going so far here?
So, yeah, so great. So, I mean, like, to your point, my first day on the job was the day that our system got delivered.
Yeah,
so our careers at this building started at the same time. Yeah, so no, it's been great. I've been loving it. The POSEIDON, I've been loving it here, but I've been loving the POSEIDON as well. It's been awesome.
Yeah, and the role of application scientist. So you help kind of develop some different, run different samples and think about new places we can use it. Also run some samples for customers.
Yep. Yeah, absolutely.
So do a little training here and there.
That's right. Yeah. Little training, little demo stuff, little technique development. Try to figure out how we can use it and how we can branch out and make sure that the right industries know that we exist. So
And speaking of branching out, so I have a little story to tell. And one day, so I'm all, you already know what I'm going to say. So one day, most days, so I'll walk in, kind of, Billy and I, hey, what's going on? Well, what does Billy do? He comes in, hey, John, I got this great thing. It's so awesome. You're from Wisconsin. I'm like, yeah, I'm from Wisconsin. Okay, well, then you're going to love it. And what does he do? He pulls out this little thing, Door County cheese curd bites. Well, come on. Have you ever met a Wisconsinite who had turned down a cheese curd? Well, then they're not a real Wisconsinite. Man, I tell you, I put this in my mouth. Worst thing ever. Don't do it.
Yeah.
I mean, I appeal to Everlasting Eats. Don't make these.
Clarify, it's a freeze-dried cheese curd, though.
It is a freeze-dried.
Yeah.
And it is just so terrible. Like,
freeze drying completely changes, which is part of the reason why we do this. But freeze drying completely changes the texture, it changes the taste, it changes the experience. In food products, it changes the experience for the consumer. Yeah. In drugs, it changes the impact and how quickly it gets ingested into your system. So freeze drying is very important. I saw these at the store. I didn't see it as a fun treat to have. I saw it as like, I'm definitely going to buy that. I'm going to spend my own money to bring that to work so I can scan it.
And yesterday, as we were getting ready for today's show, Billy pulls them out again, and we all try one because nobody could believe me how bad these things taste, right? And he pulls them out, and I think we had a pretty uniform response here. I think the description was sawdust. Now, the question though is okay. So what did we feel about this? Well, okay. I think the uniform feeling was it tasted like sawdust, and we also felt that there was an overwhelming, like, weird saltiness to them. Mm-hmm. So I think what we might be able to do is take a look at your computer where we happen to have it pulled up, and understand some of this origin of this very dry, sawdusty flavor, and also the saltiness, right?
Yeah, absolutely. So whenever we're scanning price, so this is a freeze-dried cheese curd. And you can it looks like it tastes amazing right in this picture. So you can see, one of the things you can see,
look dried out.
You can see on the outside some of the brighter bits that look kind of crusted on there.
Yes.
That's the salt.
That's the salt.
Because
the brine.
And then and so also to be clear, we are in one of the softwares in our software suite. This is called CT Vox. It's our 3D viewing software. Mm-hmm. So we can adjust the grayscale. Oops, wrong button. If I hold down Shift, I can slice through and I can look through the internal components of my sample. You can see, so freeze drying is all the moisture has been removed from your sample, right? So, and what's interesting is you can see along the edges all that salt that's been accumulated or crusted along the outside of the edges of your sample. See, like, one thing that's interesting is right there's like a little vein of salt in this cavity.
And it looks so wrinkly and dried out.
It does.
And that's how it tastes out there. So anybody watching, just
steer clear of freeze-dried cheese curds.
It'd be fun it's fun party joke.
Yeah, exactly.
On your friends.
Exactly. That's the only thing I've used it for so far. I've scanned it, and then I've made people eat it when they come into my lab. That's all they've been used for.
So freeze drying. I mean, that is though a big topic for some applications. So pharmaceutical applications, it gives a lot more surface area. Yeah. So you can get a higher uptake of the APIs, and it's also used, of course, in the food industry.
Yeah, and I mean, most people have had like freeze-dried ice cream, like astronaut food, right? Yeah. They always sell those. It's fun. Candy companies are starting to experiment with that as well. It changes the experience for the user, for the consumer. Yeah. It can be very impactful understanding the amount of surface area that you have inside, the amount of void space that you have inside your sample.
Yeah. So cheese curds, eat them fresh. Nice and squeaky. Eat them deep fried. Many different ways to deep fry.
That's right, yeah.
I would not recommend freeze dry. So let's take a look at some of this other stuff we got. So now this is kind of interesting. This is like a little metal piece.
Yeah, so I was at a 3D printing conference earlier this year, and there were things, so these are two 3D printed things right here.
Okay.
This clear plastic one is a resin printed piece. This metal one is a Inconel metal printed piece. So, and one of the things I was curious about with the new Poseidon, I wanted to know kind of what that limit was, what that upper limit is. We can do metals.
Yeah.
Inconel is very dense. Can we do Inconel?
Well, I mean, yeah, I think conventional wisdom would go, the line is here, this is okay, this is a no-go.
Yeah. Yeah, I mean, and so I wanted to know. Now, look, this is a small piece, right? So if you have a really big piece of metal, you know, where is that limit? How big of a piece can we do?
It's small, but the bottom is really quite large.
Yeah.
And even the top laterally. How did it work out?
Yeah.
Let's take a look.
We can take a look at the sample. So,
wow.
One of the things they did with this sample is they wanted to see, they printed it with 3 different infills. So you see different support structures throughout the sample. And then again, if I hold down Shift, I can left click and slice through. So we can see all the different infills and structures, and you can see how well they did with their 3D printing. And then we can also see that there's all these voids inside, right? Of course, like there's going to be voids inside. So whenever they do 3D printing, there's this material that they lay down, and then they print out whatever the structure is, and then they clean out the material, the fill material. So
what's also very interesting to me is how, when you look at it at that magnified scale, you get a sense for the roughness. Because when I'm looking at it here, that really doesn't stand out to me.
Yeah.
But here, we can very clearly see how the particles
are
centered together.
So yeah, and to your other point, we do see it is a little difficult for for the Poseidon. Our highest kV is 110 and 16 watts on the Poseidon. So it is a little difficult to get through these denser parts, but if there's damage in here, you could definitely still see that.
Yeah.
And then also we can see the roughness, like you were saying, on the support structures. But then also we can see something else. So in the other software, we have another software called CTN where we can do analysis. I was able to extract the void volume, and then we can now display that void volume. And then if I hide that and hide that, so now what we see, these are all the voids extracted. Now I have them colored. I have them colored by the thickness of the void. So where it's blue, the void is thinner. Green is thicker, and then there's red. Where it is red, that's going to be your largest voids.
So why didn't it identify the voids in the middle?
So what we see here is this is void here, and this is still low density compared to the structure, but there's no void present there. So what this means is that there's material in these voids that never actually got washed out. So if this is something that's important in your manufacturing process, knowing that your fill, your material wasn't able to wash out or wasn't able to get cleaned out is, maybe that's impactful, maybe it's not, but either way, it's good to know how well your process is working. So
well, that's a very important point for that 3D printing is that infill, right? In some areas it's closed off, or it's too small, the interconnection, and you can't get the particles out. So that's really cool. And I am just absolutely astounded that you could shoot through it. And the bottom, I mean, for everybody, the bottom of that thing is probably like, what, a good 2 centimeters in the short axis, and the long axis, we're probably talking like 3-4 centimeters.
So
that's a lot of Inconel to be actually even getting data. Like you said, if you saw a crack in the bottom, you'd be able to see it. Now,
exactly.
Moving on to your other example. Now here, on one hand, we'd go, well, I can see through it. It's clear. So I see these channels.
Yeah.
What does XRM bring to the table beyond I can already see through it?
Right, yeah. So this piece is it's a resin 3D printed microfluidics chip. And like John was saying, so the way I have it here is it's not clear on here, but it has these channels that were 3D printed.
Okay.
And so what I wanted to know, the same 3D printing conference, what I wanted to know was how uniform can a resin 3D printer print these channels? So if you're trying to flow through this, your channels, they need to be open. So first off, is it open all the way through? How good of a job did the resin printer do? And then second, how consistent are these channels? So we were able to, obviously first we were able to image this, and I mean, we're getting really good clarity and contrast. You're able to see the openness of the channels here. But then also, again, I did the analysis and I applied a thickness mesh. And so now we're able to actually visualize how consistent those channels are. so I think that's really interesting. And hang on, I think I have this, if I'm not mistaken, if we add in our cutting and clipping shape, and then we can bring that down, we can, hang on, never mind, that's not going to work.
And,
like
when you're setting that up, so one thing that was kind of interesting too about this sample, correct me if I'm remembering incorrectly, but when we first got it and we threw it in there, we measured it, and the channels looked a little weird. And we couldn't figure it out because there was like these little blockages almost. We're like, oh, it's blocked. But what it turned out, there was just some residual liquid.
Right.
And so then what we did is just put some air on it and blew those out, and then all of a sudden we could see that it was nice and cleared out.
Yep.
So something that optically we did not see. We could see the contrast because of that density differential with the XRM.
Right, exactly. And the cool thing was, in XRM, like you're mentioning, there was fluid inside of there. We couldn't see that really, but in XRM we could see there was something there. So the cool thing, in my opinion, is it's a fluid, but we were still able to see it in XRM. Yeah. So that's one thing that a lot of people ask is, like we have rocks up here, for example. A lot of people say like, well, if I have a rock that has been saturated with something, would you be able to see the fluid? And generally speaking, yeah, it depends on the fluid, but like I've done it where we've had like a light oil inside of the rock, and you can still see that oil trapped inside the pore space.
So another cool thing about this as a technology is there's a lot of these new machines out for doing laser scanning. I mean, heck, even like most phones nowadays have like a LiDAR scanner and things like that, so you can do 3D model of the outside of things. But in this case, you can really image that channel, and you can understand things like the roughness of the channel. Yep. And that's key to this application, because when you're talking about the mixing, it's important to understand how much viscous flow versus laminar flow you have going through it. That tells you about intermixing and things like that. And that is also definitely connected to the print quality.
Right.
So if that starts changing, it could change how this product works.
Yeah, so if we go back to the 3D image we're looking at here, depending on your, like you were saying, depending on your fluid, if you have a really viscous fluid, maybe this isn't going to matter as much, but also depending on the 3D print, the resolution of your 3D printer, it's going to change how smooth and how consistent these channels are. And if your channels are really rough, then maybe your fluid or whatever it is won't mix as well. So being able to visualize that surface roughness as well is going to be really important.
Yeah. I don't know if you can cut it like
from
this side so we could see a cross section maybe. The other thing that's really important for this, which is kind of cool for the X4, or any machine that has multiple detectors, is that you can measure it on different length scales.
That's right.
So if you want to get the whole overview, you switch over to something like a flat panel, and then bam, now you got the whole picture. But now if we want to focus in and get better resolution on those channels and see that roughness, switch over to the CMOS, and you can get that.
Yep.
So
yeah, being able to go to the CMOS detector and get that much higher resolution can really be beneficial.
All right. So now we got two things here, and we got two rocks.
That's right.
Two rocks.
Yes.
And one of these, is this like what, petrified wood or something?
You know, it kind of looks like it. It is a fossilized T-Rex bone.
What?
Yeah. So look.
Wait a minute here.
I was at a conference.
T-Rex.
Yeah, I was at a geoscience conference.
Yeah.
And it said they had fossilized T-Rex bones. I was skeptical.
Yeah.
But again, much like the cheese curds, I spent my money. I'm not going to say how much. I spent my money.
Yeah.
Because I was like, come on.
Yeah.
This just looks like a normal rock, right? And I'm a geologist, and I'm looking at this, and I'm like, I don't know, yeah, sure, maybe. Yeah. So I wanted to scan it and see, is it really a fossilized bone? Number one, and number two, what does that look like structurally? Yeah. Like, what are we looking at internally for that? I had no clue. So yes, we did it. But yeah, so T-Rex bone. I thought it was really interesting. But yeah.
I don't know. Is it interesting?
Let's take a look.
Let's find out.
So here's our fossilized T-Rex bone. Yeah. And again, just kind of looks like a rock. It doesn't, honestly, it does kind of look like petrified wood.
Yeah, it has that like porosity.
Yeah, exactly.
Are you sure?
It kind of looks like tree bark.
Pulling your leg here.
That's what I don't know. Yeah. But now if we hold down our shift button and slide through,
Wow.
so we can actually see these are fossilized, or this is where the blood vessels were.
Do we have any blood that we could extract?
No.
And maybe start a new project here?
No.
Hey, Brooker does have a lot of life science technologies under.
Brooker's going to open up our own Jurassic Park after this.
I was trying not to say the words, Billy.
Oh, my bad. I'm sorry. But yeah, so this is what we see. But yeah, I mean, like, so basically when we're looking at it like this, and let's go the other direction as well. Actually, let's do this. Let's show our cutting and clipping shape. So we're going to cut this area out. And again, I did my, oops, wrong one. Cut. I did my thickness analysis on the sample here, on the void space here. And so what we can see is we can see where the blood vessels were.
Yep.
Let me turn that off. Turn that off. So now we have a thickness analysis on the blood vessels, fossilized blood vessels. So it's really interesting. It's interesting to see the structure that was left behind.
Yes.
In this what is now rock.
Yeah. And so the color here now, the red areas, that would be where it's a bigger void.
Yep.
The blue is the thinner void.
That's
and
right.
It's really neat how you can see that directionality too. If we look at that flat plane, there are little circle holes, but against the other side we see more of those lines.
That's right. So if I turn that off, if you look at it in this direction, or in this way without the structure's thickness there, yeah, you can see the just the circles, right, and then you can see the vessels going up and down.
And it's really amazing. Like, we pick something like this and we run it, and it just talks to me about that fundamental science, which is you ask a question and you answer the question. So, what does it look like if I measure a T-Rex bone? You measure it. And what does it do? It doesn't necessarily lead us just to all the answers. It answers one question, but now I've got like 10 other questions. Like, what would it look like if we got some petrified wood?
Yeah, exactly.
What would it look like if we measured the bone, not necessarily the fossilized bone, but real bone, right? Would it look similar? So it just leads to more and more questions on that fundamental level. And that's cool.
It's a good thing. It's a good thing, and it's a problem as well, because now I've answered one question, but I've asked 3 more.
So, it's always anticipating that unasked question, right?
Yep.
And now here we have a little bit more of a classic sample, like from your past life.
That's right, yeah.
So a geological core.
Yeah, so one thing I like to point out about this is, or one of the reasons why I brought this specific, it's still set up for me to run scans. Yeah. And the reason I brought it in like this is I wanted to show one thing people often are surprised about is you can stack samples together, or they just don't think about it maybe. So I have 2 samples, I have 2 rocks here stacked together. And so you can stack samples together and run 2 at once, and then you can then you're good to go. You have 2 done, and you can move on. So instead of just you run 1 scan, you have 2 samples done. So I like having this to show. And then as far as rocks go,
one question about the sample.
Yep. Sorry. Yeah.
I noticed on these you have this foam under them. This one we have like a white foam. This one we have like a pink foam. Why do you put the foam?
So these bases are metal bases, and I want to lift my sample away from the metal to avoid scanning artifacts. Okay. So this is styrofoam, and this is some kind of like, it's like a dense or more substantial construction foam. And so I have them lifted away from the metal base. The styrofoam and this other foam, they're more X-ray transparent, and I have them wrapped in parafilm. Okay. So, which is also very, very low density. So depending on your material, if you're at a high enough kV, it's going to shoot right through these, and they're going to be X-ray transparent. So, and it avoids scanning artifacts. It helps make sure that you're only imaging your sample without any artifacts or anything to mess it up.
But one thing is essential is that sample can't wiggle.
Right. Yeah. Number one, the first thing I say in all my trainings is your sample has to be stable. I don't care if you know how to use the scanner. Anything beyond that, like if you have the wrong scanning settings, you could have perfect scanning settings. It doesn't matter if your sample's moving during the scan. So it's garbage in, garbage out. Yeah. So if you have a bad scan, it leads to bad reconstruction. If you have a bad reconstruction, it leads to bad analysis. So it starts at the very beginning, And as simple as it sounds, sample prep is probably the most key thing.
Yeah, and there are corrections. There's corrections for a lot of things,
right?
Especially in today's world of AIs and all this other stuff. You can correct things, but it doesn't replace fundamentally good data.
Yeah, exactly.
Right? So really stable mounting, the foam on top of the high-density post, and then the parafilm to really secure it down.
That's right. Yep.
Those are great tips. Okay, let's take a look at the actual analysis now of that core.
Yeah, so this is a rock. This is a Benheimer sandstone. And then, again, shift, and we can slice through, and we can see inside of our rock. So maybe it's a little dark. We can lighten it up there. So what's interesting is one of the reasons I like this rock is we can see, sorry, I'm a geologist. Hey, it's just a rock, but hey.
Don't apologize for who you are.
I think it's cool, man. There's a lot of different grains in here. There's a lot of different mineralogies in here. So there's a lot of good contrast in here, so it works really well.
Yeah, it's neat. I mean, I see kind of this there's like the overall almost brainy looking bit, but then there's these inclusions, these chunks in it,
That's right, yeah.
Okay. And we can see there's a color difference, and the color difference comes from
the different densities of the different mineralogies. So we have the different minerals in here, the different grains, and so those are gonna have different attenuation values. So again, let's take out our chunk here, and let's see our void space. So again, once again, now one thing that's really interesting about this analysis is in our analysis software, I told it to keep only the largest connected volume. So anything that's connected in the pore space, only keep that.
Now, is that important for this kind of rock, for the application?
Yeah. So if you're interested in fluid flow properties, whether it be oil and gas, if you're looking at an aquifer or something along those lines, so groundwater studies, this is going to be what the connected porosity is going to be really important for flow. So if it's all connected, that means that there's a pathway. If it's disconnected porosities, then that's going to be more difficult. That's where, so in like the oil and gas world, that's where like fracking would come into play. But if you have all this disconnected porosity, that's where it can be a problem. It depends, right?
Depends what your application is.
Depends on what your application is.
And by the way, if anybody has questions, go ahead and type those on the side of your screen over in that YouTube chat, and we will answer them live once we're through these samples. So.
And another thing I like to mention that has come up a lot when I talk about rocks. So there's
not geological specimens. They're rocks. I was educated on this because I'm a metallurgist, and I remember when I started, I was doing an app note or something on a sample, and I go, geological specimen, and one of the geologists on our team goes, John, it's not a geological specimen, it's a rock. All right, let's take a look at the rock.
Let's look at the rock, yeah, and what a wonderful rock it is. So one of the things I like to point out to people. Yeah. So a lot of people, when you're doing analysis on these plugs, something that always ends up happening is, or one of the analyses that ends up happening eventually is you're going to get a thin section made, and you're going to take that thin section, you're going to put it into the SEM. Whether it be for, like, you want to better understand the pore space, or whether you want to understand, it's not always about what the minerals are, it's where the minerals sit inside the rock.
Okay.
So that's where like SEM analysis on rocks comes into play a lot.
But your field of view in that type of analysis is a little bit smaller.
Right, much smaller.
Okay.
But what you can do here is, let's say this is the plug you want to look at. Well, you can see I'm just kind of moving around. I'm just kind of scrolling around, and you can see all the different features. Like maybe this is some clay stuck in the pore space. These are high density grains that you might be more interested in. You can see this really wide open void space. Maybe you're interested in specific areas of porosity. So what you can do is you can find the spot. You can take a 3D scan. So now you have this 3D scan of your rock, and you can find the spot that you want to slice down to and make your thin section at.
And that's kind of cool too, is that a lot of times when it comes to getting samples, whether it was this T-Rex or whatever, it takes a lot of effort, a lot of time, a lot of money to sometimes get that sample.
Right.
And so when you're doing a scan like this, you're really capturing that pristine condition. Yeah. So if you do an analysis later prep it for SEM, prep it for thin section, staining, anything like that, you can always reference back to this original data.
Yeah, exactly. Right? It's digital, you have it. So doing this is a good first start for whatever analysis that comes afterwards. So if you're gonna, maybe now you have this rock, you have the scan done. So now that we have the scan done, I can do any kind of digital analysis I need to do. but the rock itself can go off for, you can cut it in half and send half of it to XRD, and then the other half can go to thin section or something like that.
Yeah. So that's pretty cool.
Yeah.
Now, for everybody out there, we've been looking at these scans that Billy puts up on the screen. And I think one thing that's kind of cool that sometimes doesn't come to mind is that this is called a voxel cloud, right? So that whole space, the whole square or the cube, even if it doesn't look like there's something there, there's data there. It just happens to be a 0, right?
Right.
And then in another spot of that three-dimensional space, we happen to have a different count rate, which is that X-ray absorption. But that whole cube is what we're measuring, whether it's filled or not filled.
That's right.
So when you're looking at these, the immense amount of data is really awesome.
Yeah,
you know?
yeah. I mean, that's one thing, especially in my trainings. It's hard to get across the fact that your entire your sample sits inside of your field of view.
Yeah.
But everything in that scan is part of your scan volume.
Yeah.
So it's important to remember that everything that you see on your screen is your scan volume.
Yeah.
So yeah, it is an immense amount of data. There's an immense amount of analyses that can be done with this data as well.
Yeah, and I think that's kind of where we're at with X-ray, is we can see the data, we can take a lot of qualitative, and we're starting to find more and more quantitative places that we can go with this data.
Yeah.
And data handling is something that can be done on computers. I mean, you could do it on your laptop. For doing really complex analysis, we have pretty beefed up workstations that we use sometimes. When people say, well, 10 years ago, when I was studying geology or I was studying, mechanics, we didn't have that, we don't need it now. Well, you didn't have it because you didn't have the technology to actually look at the data.
Yeah.
Right? But we have it today.
Yep.
And so, and very affordably too.
Yeah.
Right?
Yeah.
So that's a pretty cool, amazing set. So everything from gross, disgusting cheese curd through cores and dinosaur bone and 3D printing. That's really neat. So we do have a few questions that have come in before.
Okay.
And then we have some that have been coming in. If anybody does have a question right now, go ahead, type it in. We'll get to it. Or if you're watching this later, you can send it in, live.events@bruker.com, and we will get back to you. So the first question here, we had live come in, is from Glenn. Is it just visual surface roughness, or can you measure it? So is it qualitative, or can we be quantitative about that surface roughness?
There is a surface area measurement that you can do in our CT analysis software, and I think, if I'm not mistaken, there is a roughness measurement as well. I haven't done roughness measurement, but there is a roughness measurement that can be applied.
Yeah. So I think what it really boils down to is that you can get almost every metric out of this.
Yeah.
It's just a matter of then framing it in the nomenclature that you're used to.
Right.
So sometimes RMS roughness, which a lot of people from AFMs and things like that, they get it. Here you can get you can measure the height differentials across the surface, the average ones, and things like that. You could also, like you said, measure the overall surface area versus the planar area, and that could give a measure of it. There's a ton of ways.
Yeah.
Right?
Yeah.
Actually, what's kind of neat for all of our users out there is this is an awesome opportunity to start to set the standard.
Yeah, yeah, absolutely.
And that oftentimes, when you get a tool like this, and you're the one who can establish the way that all the work is done moving forward, that's a huge opportunity. Next question that came in before our show is from Jason in Boulder. Can the X4 POSEIDON resolve internal defects in composite materials without sectioning?
Yeah, absolutely. I mean, as we're seeing here, we're looking at internal defects. Well, potentially. I mean, it could be an internal defect. I mean, like with this one, the 3D printed Inconel sample, we're looking at what could potentially be an internal defect with this film material stuck in the middle here. So yeah, I mean, non-destructive defect analysis, failure analysis is kind of one of the biggest uses for XRM.
Yeah, so, I mean, cracks, delaminations, inclusions.
Yep.
And what's neat is that you can measure a part, and because it's still in this pristine condition, you can put it back into service.
That's right, yeah, yeah.
So you can kind of, check long-term wear studies or even do better predictive maintenance on things using it. Next question from Lena in Munich, International.
All right.
So We're working on sintered metal parts. Okay, so something like that.
Okay.
How well does the Poseidon handle high-density samples without losing the contrast?
Yeah, I mean, it says so. Same example, same sample. I mean, we saw really good contrast between the void and the material, and then even the fill material. We could see that the support structure was really well defined, right, and had really good contrast, and you could see the difference between fill material and the support structure. So, I mean, right there in that one really high-density Inconel sample, we're seeing the high-density Inconel along with the fill material, and you can tell the difference between the two.
And with X-ray imaging, you're always going to have a trade-off: high energy and high resolution. Higher the energy you go to, worse your resolution is going to be. It just has to do with physics of detectors, things like that. Here we have an extreme case: Inconel.
Yeah.
Very, very high absorbing materials.
Yep.
What are some other metals, though, that we could say, we have no problem with measuring? Or where's our area of play? What's our sandbox here, in your opinion?
I've done some, I did a dog bone sample that was aluminum. Now it was only 4 or 5 millimeters thick at the middle. But that was a great sample. We could see it was also 3D printed, actually, now that I think about it. But you could see the voids inside from the manufacturing. And so aluminum works really, really well for us. We can do stainless steel. I have done some stainless steel, but again, it's all going to be size dependent.
Yeah, the thickness, too.
Yeah.
So if you have like an empty box, like sheet metal,
right,
okay,
no problem.
all day long.
Yeah. Yeah, it's the thickness of the material. Yeah,
Send me a 3-inch cube of stainless steel.
Right.
Oh, not happening, right?
Right. Yeah. But I will say we have done with our 1273.
Yeah.
There was a large, like a water pump for a car.
Yeah.
And we're able to do a really rough scan to see large voids. We're able to do that in 15 minutes. So not only get through it, but we're able to see. We're able to do it in a really fast, timely manner as well, which is nice.
Yep. And we do have corrections, too, for beam hardening and things like that. Of course, statement always goes back, try to get the right energy, try to get the right filter to minimize those artifacts.
Yep.
And one that was really interesting to me that came through was some lead sample. Right? There was that one sample. We don't have to give the specifics on it, but it was lead.
Oh, yeah.
And the tip we had gotten was, you just got to use the right energy because there's like an absorption edge. And if you come right under it,
yeah.
And it looked really good.
Yeah, that's right. Yeah, so we were messing around with that. We decided we were going to run one. We did a scan with like our highest case, so we ran at 110 kV. But then the kV, the energy we were told was something around like 87 kV.
Yeah.
So we stuck at 85, and we got this insane contrast from it.
Yeah.
So knowing your characteristic X-rays is useful as well.
Yeah, and it really comes down to that. Just try it. We'll try it.
Yeah, exactly.
You can always reach out to us. We throw it in there, see what we get.
Yep.
But even something like lead, which conventionally you'd be like, yeah, right.
Yeah.
Whatever. No, and it was thin. I mean, it was.
It was a really small piece.
But still, we could do it. All right, Marcus from Atlanta. I saw the Poseidon used for additive manufacturing. How do you deal with beam hardening when scanning 3D printed polymers?
Yeah, good question. So in our on the front end, you need to make sure you're using the appropriate kV and filter. So if you're filtering correctly and you're using the appropriate kV, then it'll minimize beam hardening in the raw scan. But then once you go to reconstruct that scan, we have beam hardening correction in our reconstruction software, which comes with the system. So we have corrections post-processing as well.
Yeah. So we talked a lot about filters and energies.
Yep.
What's the really short description for everybody out there about what does a filter do for us?
So what a filter does is if you're scanning, let's say you're scanning at 100 kV.
Okay. So you have this big old hump of Bremsstrahlung.
Yeah, you have your Bremsstrahlung curve, and if you're scanning, so 0 and then 100 kV.
And you get this there's
big
a bump.
That's right.
Of energies.
That's right.
Okay.
So if you're at 100 kV and no filter, all those X-rays from whatever, it's not 0, but all the X-rays in the spectrum are present. So if you use a filter, what it does is it cuts off that curve. So it allows you to only use the higher energy X-rays. So if you're scanning something that's of higher density and you want to use those higher energy X-rays, you don't need those lower energy X-rays because all that's going to happen is they're just going to get absorbed in the outside of your sample. So you use a filter to cut off those lower energy X-rays, just stop them. Otherwise, they're going to get absorbed on the outside of your sample. They're not going to make it through, and that's going to cause excessive beam hardening.
And so you get this, like, the outside of the sample looks bright.
Right.
And the inside looks a little dim.
Yep.
Because the X-rays can get through the outside, but not through the inside.
Right, yeah. They can only get through so far on the outside of the sample, and they get absorbed, and that's why the outside looks really bright. It's all those X-rays getting absorbed, all the lower energy X-rays getting absorbed on the outside.
Yeah, and so there's a little bit of like trial and error when you're doing this. You could go in educatedly, but we do a lot of tweaking.
One thing I've been telling, when I go to trainings, one thing I've been telling people lately is, give yourself some grace, give yourself some time. Don't worry, like you're not gonna get it right the first time. And I tell them whenever people send me samples, I always run at least one test scan, if not 2 or 3. Sometimes, I'll start putting things in my file names like try 5. It's like on the 5th try, trying to figure out what works. Exactly, what works best. So, run a quick scan at first with settings that you think might work, and then adjust them from there. If you got it right the first time, now you can run your full scan, no problem.
Awesome. All right, Chloe from Sydney, what kind of software comes with the X4 POSEIDON? Does it support automated segmentation and porosity?
So software comes, the software that you get with every system, every Bruker instrument, is obviously the scanning software. Okay. But then beyond that, you get the reconstruction software, 2D and 3D visualization, which we saw the 3D visualization here. And then there's an analysis software that can do all the analysis like we've seen here. And then there's also a software called CT Vol that allows you to look at like STL files. So if you have structure files, you can open those up, and you can open multiple and do and have kind of a visualization of those. Automated. So if your samples, there is a batch processing. If all of your samples are very similar, if they're similar enough, you can have a task list in CTN, and you can just open up your sample, open up that task list, and hit play, and it'll run through everything. So, and we do have a software that allows you to run multiple samples.
Cool. So the answer is yes. So then last question we have that came in before, Lars, we're screening ceramic filters. How fast can the Poseidon scan a full batch? And is there a way to queue those jobs?
So everyone's favorite answer, it depends.
Well, part of it is that these holders are actually from our
sample changer. Yeah, that's right.
So, and that holds how many samples?
15.
15 samples, and you can even stack them.
That's right, yeah. So the it depends part is answering the how long does it take. Yep. So it depends on the size of the sample. So like the T-Rex bone took longer than one of these rocks. Sure. So depending on the sample size.
Let's say their ceramic filters look like this.
Yeah, so if you're looking at this, and you can stack 2 together. We have a 15 position sample changer. Sure. So that's 30 samples. And then each one of these could probably run in, I think it's under an hour. So yeah, I mean, so you're looking at 30 samples in 15-ish hours.
Okay.
So that's, yeah.
And if the samples were a little bit smaller or less absorbing, what's the fastest that we could run, say, a quality control scan? Maybe I just want to run through a whole bunch of samples at once. I'm just looking at major defects.
We have a continuous rotation feature on the Poseidon, and we did I still say, if I hadn't have been there to see it, I wouldn't have believed it. But we did a core plug, a little bit smaller of a core plug than this, and in 2 minutes.
Wow.
And that was we were able to do quantitative analysis on it. It was the amount of detailed contrast that we got on that was insane.
So you could see then if there's inclusions, if there's a crack in it, if there's a problem like that. You could do it that quickly.
If you look at our Geo app node under the Poseidon online, the top picture that shows the void space in the structure thickness like you've seen on here, and then the formation is like an orange.
Yeah.
That's the 2 minute rotation scan. It was awesome to see.
And so that's all the questions. Oh, we have one that just came in here. How does the system compensate for beam hardening from filtering out the lower energy X-rays? Does that happen in the hardware or software? So how does it do the beam hardening? How do you do that?
So in the software, in the scanning software, what's nice is we have an automated filter changer.
Mm-hmm.
So when you go, let's say you go to 80 kV, you select what filter you want to use, and then it just automatically slides over in front.
Let's say you collect the data.
Yeah.
You look back on it and you go like, the outside looks a little brighter, the inside looks a little darker. How can we fix that?
So that in the reconstruction software,
Mm-hmm.
we have a beam hardening correction. It's an algorithm that's built into the reconstruction software. So basically, you say that you want to correct for beam hardening, and you give it some parameters, and it steps through those corrections, and then there's a profile line that you can draw. So you can, from that profile line, you can see when you're undercorrected or when you're overcorrected. So if you're undercorrected, the outside's going to be brighter. I'm thinking about like a circle. The outside's going to be brighter, and the inside's going to be darker. So you're going to see like a U shape.
Mm-hmm.
If it's overcorrected, the outside's going to be darker, and the inside's going to be brighter. So you're going to see like a hump. So you want to get that profile line nice and flat.
Okay. So yeah, so you do that in that reconstruction software.
Correct.
All right. But it's always best to do some quick shots, especially these 2-minute scans. Do some of those. You're going to see those beam hardening effects fairly quickly.
Yeah.
And so really, before you do the longer scan, get the best KV, best filter combination.
Right.
Going. All right. Another question from Glenn. If you run the machine for 10 hours straight, will there be any accuracy loss? Does it heat up?
No. It does heat up, but not like you're thinking probably. It gets a little warm inside the cabinet, maybe, I don't know, 70 some odd degrees.
Yeah.
Like it gets slightly above room temperature is what I like to tell people. So personally, I've done a lot of candy bars in my day.
Yes.
So
cheese curds and candy bars.
Yeah. It started as a recommendation.
Yeah.
And then to run a Snickers. If you haven't done it, run a Snickers. It's amazing.
I swear, I only bought the whole bag of kid-size Halloween candy because I was going to measure one. Well, Billy, why are there all the wrappers out? I don't know.
Yeah. Look, I tried handing it out. Nobody wanted it. At least that's what I say.
I had to eat it.
So
It'd be
yeah.
sad.
But yeah, I've done something like, I'm serious. I think it's like 25 different candy bars, and I've only had one melt.
Yeah. And
it was a candy. I wasn't familiar with it.
So in NRecon though, there is also a thermal drift correction, right?
Yes, and in Recon there is a thermal drift correction. So, yeah. So that's if you're thinking about like, I would say like so thermal drift correction helps a lot if your sample moves from poor setup. But then also like if you have something like a low density plastic where it can expand at just above room temperature, 75, 80 degrees. If there is any kind of expansion or contraction or moisture loss, like we've done like apple. I've done an apple seed before, and in the scan you can actually see it shrink. So if you do have any like moisture loss or something along those lines, the thermal drift correction can help to some extent.
So yeah, and what I think it's after 2 minutes, or is it 10 minutes? If the scan is longer than a certain amount of time that I think you can configure it in the software.
Yep.
It'll automatically correct a series of scans. So what it'll do is, it'll measure, and correct me if I'm wrong here, but my impression, it takes your normal scan. And let's say that you do something really long. Like when we were first coming out with this Poseidon, I was measuring this starfish. There's like a bazillion scans of a starfish. And how long can I do this? And I set one up, I remember, for like 3 days over a weekend. And what it does is then it'll collect your data, right, the turning. And then at the very end, though, it's going to collect just a series of like big steps, every 15 degrees or something that, 30 degrees. And then when you go into NRecon, you go up, file correct, or file thermal correction. There's a setting up there. And then what it'll do is it'll reference those scans against your data, and it'll automatically fix your data.
Yeah.
And it can do that in X and Y shifts, but also in zoom and rotational shifts.
Right.
So that's a feature in NRecon.
Yeah, actions XY alignment with a reference scan. So it compares the projection during the original scan, like you said, with that projection at the end of the scan from the same position.
Yeah.
So any movement from during the scan to the very end of the scan, it can correct for that.
Yeah.
Yeah.
So, so that's how we do that, Glenn. All right. That's all of our questions. So thank you, Billy.
No problem. Thank you. Happy to be back.
Yeah, I mean, look forward to seeing some more examples and doing some more scans. This technology really always amazes me at what we can do.
Yeah.
And how we can see it. It is just one tool in our toolbox. You know, we talked about SEM, we talked about XRD, we talked about XRF. All of these things together give you a very beautiful picture of it, but XRM, I think, has become one of those really essential technologies in the whole toolkit for every lab. So thank you, everybody out there, for joining us. And until next time, make sure to keep your signal high and your background low.